Now let's consider some other simple two-terminal elements. This we will just look at the characteristic now, and we will analyze circuits with capacitors and inductors later. But if I look at a capacitor like this and define the voltage Vc in this, as usual, I have to look at the current in this direction. So again, it doesn't mean the current will always be flowing this way. This is the current that I will measure. Okay, even to measure current, I have to choose some direction, and this is the direction that I am choosing. And you know that IC will be some parameter of the capacitor C times the time derivative of the voltage across the capacitor. Okay. And if I invert this, I can write the voltage across the capacitor as 1 over C integral IC dt. Okay. Now, one of the things about the capacitor that distinguishes it from a resistor is that the value of the voltage across the capacitor depends on the current not at the present time but all of the past time. Okay. Whereas for a resistor, the voltage across the resistor at any instant is dependent only on the current at that instant. Okay. V equals IR is true even if V and I are varying with time. For each instant, V will be equal to IR. That is, the current at each instant will depend only on the voltage at that instant, or the voltage will depend on the current at that particular instant. Whereas the same is not true for a capacitor. The voltage across the capacitor depends on not only the current at the present time, but also the history of the current. Okay. Now, this is the definition of the IV relationship of a capacitor. And because it is related by this derivative, we cannot plot I versus V. Okay, we can do that only when the element is memoryless. That is, the current and voltages are related only at that instant of time. That is, current in that instant is related only to the voltage at that instant of time. Okay, but this gives you the relationship just like we did for the resistor, except that it's a slightly more complicated. It's a derivative. Now, my first question to the participants is the capacitor linear or not? I have a number of responses. A majority of them say that it is not linear, or a couple of people said it is linear. And somebody asked if I versus V is a straight line. Like I said, we cannot plot I versus V for this, because if you think about it, that is possible only when the voltage at this instant of time is related to the current at this instant of time. Okay. In this case, that's not true. The voltage at this instant of time depends not only on the current at this instant, but also on all the previous instants of time. Okay, on the history of the current. So we cannot plot I versus V, but we can still test for linearity. How do we do that? Let's say I apply V1 across the capacitor. There will be a certain current I1, which will be C times the time derivative of V1. Okay. Now, first of all, I am assuming that this voltage is varying with time. Now, if it's not varying with time, the formula still applies, but the current will be zero. That is, if you apply a constant voltage across a capacitor, there will be no current flowing through the capacitor. So, the more interesting thing is when the voltage across the capacitor is varying with time. If that's the case, the current will be related to, or it will be proportional to the time derivative of the voltage. Okay. Now, instead, if I apply V2, the current, the new value of the current will be C times dV2 by dt. And finally, I could apply the two together. Okay, exactly the same experiment I did with the resistor earlier, V1 plus V2. In this case, the new current would be C times d by dt of V1 plus V2. But the time derivative of sum of two quantities is the sum of individual time derivatives. Okay, so clearly the responses are sum of individual responses and linearity is indeed true. Okay, so this is how you test for linearity. I applied V1, found the current. I applied V2, found the current. I apply V1 plus V2. What I say is that the current will be the sum of the individual cases and a capacitor is therefore a linear element also. Okay. The IV characteristic may be more complicated than that of a resistor, but it is still a linear element. Okay. I hope that is clear. Now there were some comments. Somebody said that it is not a dissipative element, that's why it is not linear. But it has absolutely nothing to do with whether it's dissipative or not. It only has to do with whether the IV relationship is linear or not. And it is a time derivative and it happens to be linear. Okay. Again, let's look at a simple construction of a capacitor. The way this is made, again, this is just a depiction. The practical capacitor doesn't have to be made like this. It just has to have two conductors which are separated from each other. And two terminals are connected to it, A, B, A and B. Okay. I described the capacitor by its IV relationship, but I think you already know what it is. If I apply a voltage across the capacitor, what happens is, so let's say this is certain V, on the upper plate where this V is applied, the positive terminal of V, the plate connected to the positive terminal of V, there is a positive charge, there is a charge, I mean that whether it's positive or negative depends on the value of V. The charge depends on this voltage V and it's given by C times V. And similarly on the other plate there will be an equal and negative charge and that will be minus CD. Okay, if I call this terminal A, this is QA and QB. Okay, so what a capacitor does is to store charge, and the stored charge Q equals C times V. Okay. Now first of all you have to interpret properly what this stored charge is. This means that on one plate there is plus C times V and on the other plate there is minus C times V. Which is plus and which is minus, that depends on which is the plus terminal of V and which is the minus terminal of V. Okay. And also this relationship Q equals CV, you see that this is somewhat similar to V equals R times I. Okay. And this makes linearity even more obvious. Okay. Now how do we get the relationship between I and V? We know that the current is rate of change of charge. What happens is as this voltage changes, the charge on the upper plate changes. And how will it change? The way it will change is by drawing current from this wire or pushing current into that wire. Okay. This charge has to come from somewhere and it has to come from this wire. That means that the current in this wire will be dependent on change of voltages. Okay. And the current will be the rate of change of charge, which will be C times the rate of change of voltage. Okay, so that's how it comes about. And from this relationship, if you plot Q versus V, it will be a straight line passing through the origin, and that will be a linear relationship. And the IV relationship is simply the time derivative of this. And time derivative is a linear operator, so that relationship is also linear. Okay. So a capacitor stores charge Q equals CV and that's a linear element. Any questions about the capacitor? Okay. Now my next question is can the voltage across the charge change instantaneously? The question is, can the voltage across the capacitor change instantaneously? Now, I think one person said yes and a number of people said no. My question was, can the voltage across the capacitor change instantaneously? That is, can it be one value and then suddenly change to another value? Okay. Oh, it is possible. Normally you hear that a capacitor holds its voltage and it cannot change instantaneously, but we have to qualify that. Okay. If it changes instantaneously, what it means is that if you plot I versus t, it will be 0 and here it will go to infinity and that is denoted by an impulse and then it can go to 0. So what we really mean is that if the currents are finite, the capacitor cannot change its voltage instantaneously. Okay. An instantaneous change in the capacitor voltage will demand an infinite current, and that is will demand an infinite current. So if the currents are restricted to be finite, then it cannot change its voltage instantaneously. So if you allow an infinite current, which is not practical, but in theory it is possible, then the voltage can change instantaneously. And one way is, if you have a voltage source across the capacitor, and the value of the voltage source changes instantaneously, then the voltage across the capacitor has to be exactly equal to the voltage across the voltage source and it will also change instantaneously. Okay. But in this case, what happens is an infinite amount of current will be drawn at the instant of the voltage change.